If we've got a wheel with a string wrapped around it several times, moment of inertia is given to us, radius given to us, the free end of the string is connected to a block. If the system is released, what acceleration will the block have? First, draw your forces. Next, Newton's second law. Solve the equations for the unknown. The extended body diagram, we've got two force diagrams that we need to draw, one for the pulley and one for the block. Wheel has its own weight, so the pulley has its own weight. This is not an ideal pulley, so that means it's not massless. Could also mean there's friction involved unless it tells us that it's a frictionless pulley. But because it's not an ideal pulley, the pulley has its own weight. The weight is acting at the center of mass. Also, the axis exerts an upward force to support the pulley. It has to be attached to the wall. So if you want to think about it as being a pin, and that pin is pushing upwards, otherwise this pulley would just fall down under the weight of this block. Finally, the string is going to exert a downward tension force on the wheel's right side. If I had to guess for the force that you're going to miss, if you were drawing this out, it's going to be this upward force. If all of your net force is downwards, then your object is going downwards. Don't forget about that. So this upward F-axis force has to be equal to your tension force and your weight force. The block has its own weight, mg, helping it downward, and an upward tension that's opposing the downward motion. But in this case, the tension is going to be smaller than the weight of the block. So that way we have a net acceleration going down. And that tension here is going to be the same tension here. Remember, one string, one tension. They're equal, even though they're going in the opposite directions. The net force equation, the center of mass of the wheel does not accelerate, so if we write a net equation for that, it would just equal to 0. But the block's center of mass does accelerate, so when we write that equation, the stuff that makes it go, mg, minus the stuff that holds it back, the tension, equals mass times acceleration of the block. Our net torque equation, the wheel's rotation is changing, so there is a net torque. No torque on the block because it's not rotating, but the pulley is rotating, so the torque going down minus the torque going the opposite direction. So a word about directions with torques. We, by convention, normally will take counterclockwise torques to be positive and the clockwise torques to be negative. So if you do have both acting on the same object, you'll take your counterclockwise as positive normally, and then your clockwise as negative. So when you add up all of the torques, which in this case is only brought on by our tension force, because that is the only force acting perpendicular to the axis of rotation, the wheel's weight and axis force produce no torque. They are directed away from the axis. So R times F equals I alpha. Never say the block's weight is what produces a torque on the wheel. This is because the block's weight does not act on the wheel directly, but the tension does. If it was just the block's weight, then that means that this string has no tension in it, and that just doesn't make sense. Instead, we're looking at exactly where the contact is happening. That tension force is pulling down on the pulley, generating that torque. Writing the two equations, we have stuff that makes go minus stuff holds it back equals ma, and then R times F equals I alpha. Starting with the torque equation, we know that A equals alpha times R, or alpha equals A over R. The moment of inertia was given to us as 0.12. Radius was given to us as 0.2. And the radius again, 0.2. So we can solve for tension again, and guess what we're going to do with that tension? We're going to then plug it into our Newton's second law for translational motion equation. So the best we can do when we solve this is get 3 times A, take that, and plug it into Newton's second law equation. Acceleration equals 4 meters per second squared.